Sound waves are longitudinal waves. Sounds are produced by matter that is vibrating. When you talk, your vocal cords vibrate back and forth to produce sound waves that travel through the air to someone's ear. A sound wave is a longitudinal wave made up of repeating high and low pressure regions moving through a medium. In the Engage lesson, you observed a video that showed sound produced by a tuning fork. When a person strikes a tuning fork on the sole of their shoe, the ends of the fork begin to vibrate back and forth. As the metal from the fork pushes out, it pushes particles of air together into a region of higher density and pressure called a compression. When the metal from the fork moves back, a region of lower density and pressure is formed where air particles are further away from each other, called a rarefaction. The particles of air move back and forth from the rest position as the energy passes through the medium. Recall that in a longitudinal wave, the particles of the medium move back and forth parallel to the direction that the energy travels through the medium. Sound waves travel out in all directions within the medium. From the source. What is shown in the diagram represents just one area of the medium. Tuning fork and air particles vibrate back and forth from a rest position. Compression, rarefaction, wavelength. Energy moves in this direction. As longitudinal waves, including sound waves, have characteristic properties of frequency, wavelength, all longitudinal waves, including sound waves, have characteristic properties of frequency, wavelength, and amplitude. The wavelength of a longitudinal wave is the distance between compressions or the distance between rarefactions. The frequency of a longitudinal wave can be determined by counting the number of compressions or rarefactions that pass by a given point over a set amount of time. Recall that the maximum distance the particles of the medium move from their rest position is a wave characteristic called the amplitude of a wave. For a longitudinal wave, the amplitude refers to the regions of the highest density and pressure compared to the original density and pressure of the particles of the medium. The amplitude also refers to the regions of lowest density and pressure compared to the original density and pressure of the particles of the medium. Longitudinal waves can also be represented with a simple mathematical wave model that shows the alternating changes in pressure. The crest of the mathematical wave shows areas of higher density and pressure. The troughs of the mathematical wave show areas of lower density and pressure. Sound wave model showing particles of the medium. Wavelength. Simple mathematical model of a sound wave, pressure versus distance. Wavelength, amplitude. Be careful not to get confused when looking at the simple mathematical model for a sound wave. The simple mathematical wave model is shaped like a transverse wave, but sound waves are longitudinal. The mathematical model can be helpful when we want to explore changes in frequency, wavelength, and amplitude of a sound wave. But the mathematical model does not show how the particles in the medium are moving. The mathematical model does show the regions of high and low pressure among the particles. An oscilloscope is a tool that can help us visualize sound waves. The oscilloscope uses a microphone to convert sound waves into electrical signals. The electrical signals are then displayed as a dynamic mathematical waveform that can allow us to view the changes in the frequency and amplitude of the sound waves. Stop and check. How are sound waves produced? What is a sound wave? How do individual particles in the medium move in a sound wave? How is it similar or different to the movement of energy in a sound wave? What is an oscilloscope? How can it help us visualize sound waves?